Hello everyone. Today we are going to talk about video object segmentation. Before diving into the main topic, let's start with something we are familiar with: pictures. Since we are all taking the deep learning class, I assume that you all know that CNN can be used for classification tasks. Here I also want to mention Region Proposal Network, a network structure that does object detection. It works literally by proposing regions that could contain objects and keeps the most likely ones after comparing with ground truth bounding boxes. Segmentation is just doing a similar thing in pixel level, basically assigning each pixel to be either part of an object or background. This can be achieved with FCN, fully convolutional networks. FCN differs from traditional CNN, as it replaces fully connected layers with more convolutional layers. And it does a per pixel level prediction, which just means segmentation. And of course, there can be more than just one object instance. Now let's see an example of video segmentation. You can see that for each frame, the target object is colored in red. You might be thinking, wow, it looks perfect. Well, that's true because this video is actually manually annotated frame by frame, not by neural network. This kind of video is very ideal for training and testing. So, where do I get such videos? A popular dataset is the Davis dataset. It means densely annotated video segmentation. Dense here just says every frame is annotated. The first set came out in 2016, with only one instance in each video. Then in the following year, 2017, they updated the dataset, and there are now multiple objects being marked out in each video. Before discussing how to solve the problem, let's see why video object segmentation can be challenging. Occlusion means the target object is blocked by other objects. And obviously, fast movement and deforming shapes can make the problem challenging. Last, multiple instances of a same object type can also make the problem very difficult as well. There are two types of problems, unsupervised and semi-supervised. For unsupervised, the task is to find and segment the main object in the video. This means the algorithm should decide by itself what the main object is. For semi-supervised, the network is also given the ground truth segmentation mask of the first frame as input, and the goal is to segment the annotated object or objects in every consecutive frame. Today, the two papers that we are going to present all belong to semi-supervised problem, and there are mainly two approaches towards this type of problem. The first one is called one-shot video object segmentation. In this approach, FCN is built by keeping only convolutional layers from pre-trained CNN for classification, with additional convolutional layers for segmentation. The FCN is then trained with annotated videos, frame by frame, independently. At test time, for each video, the network is fine-tuned with the first frame and segment each frame independently. This approach has the advantage that it doesn't assume little motion between consecutive frames. However, the disadvantage is that it does not explicitly take temporal information into account. Today's two papers all follow the other approach, where a recurrent neural network is used to capture temporal information. Here I also want to introduce a concept called optical flow, given two consecutive frames, with the assumption that movement is small. Then for every position, The optical flow describes both the direction and magnitude of the movement as a vector. In fact, optical flow can be represented as an image where hue represents the direction and color intensity represents the magnitude. Therefore, it can be casted into a learning problem. FlowNet 2.0 is such a network that outputs optical flow. Now let's talk about the approach that uses RNN. For each frame, the input is the frame itself, plus the segmentation result from a previous frame. To be more robust, another network can be used together, with input being the optical flow and the last segmentation. The final result is then merged from the two streams of networks. Finally, before jumping into papers, there's an important thing that I haven't covered yet: the metrics for measuring how well a network performs. The most popular two are region similarity and contour accuracy. Region similarity is defined as the intersection or union between estimated segmentation and the ground truth mask. And contour accuracy interprets masks as a set of closed contours and computes the contour-based F-measure, which is a function of precision and recall.